All right, so last talk today, and we'll try to make this a bit more interactive now. So normally I would be very annoyed if I saw a bunch of people in front of me with all their laptops out and looking at them, but today I actually would absolutely love that if you did that. So let me make the font a bit bigger. Let's see. I think that's readable. So if you could go to a repository under the Trilinos organization and click on go to the PyTrilinos2 container. So I'll do that. Come on. Well, maybe I won't do that. There we go. Okay, and if you just scroll down a little bit, I don't want you to install anything on your system. Instead, what you're going to do is you're going to click on this launch binder link down there. And then you're going to wait for like a minute or 2 minutes or 3 minutes. I hope within the duration of this tutorial, it actually will show up for you. I tried this earlier a couple of times. It came within like 2 minutes. So in the meantime, I'll continue sort of talking. But in principle, what you should be getting is exactly this Jupyter notebook loaded up in the browser for you with a pre-installed Trilinos. So Trilinos isn't difficult to install this if you take certain steps. All right, so I want a Python interface to Trilinos. And there's a couple of different reasons why you might want to use something like that. Personally, I use it for rapid prototyping. So instead of like being in this cycle of like building my code, realizing that I again screwed up or forgot a semicolon somewhere, then rebuilding again and like then getting something to work, realizing that it doesn't actually work, and then being in the cycle, I'd rather have like a very rapid sort of like response that, okay, you screwed up again and like you used the wrong function somewhere or something like that. And Python is absolutely great for that. On the other hand, I also think that there are a lot of other cool codes out there that have Python interfaces that are natively in Python that we can interface in that way. A lot of like visualization tools have Python interfaces. So that's another good reason. Finally, I think that students today probably are a lot more easily convinced to use Python than to get started with C++. So this is sort of like, well, here's the entry doc. Oh, you can use Trilinos. It's really easy. And then we make them write C++ afterwards. All right. So generating a Python interface for C++ code in principle is really super easy. And one of the sort of like classical tools for that, that's PyBind 11. And this doesn't scroll well at all. So, I mean, here's an example from their documentation, essentially like a really simple two-line function in C++. Then here's the, if we want to wrap this to Python, we essentially like augment this a little bit with this sort of little macro down here that in the end will compile into a Python module that you can then just load in from your Python interpreter. So that's great. That's really easy to do. And in principle, we could like go through Trilinos and do this for absolutely every function, and it would take us absolutely forever. So we don't want to do that. Rather, we want an automated solution that does this for us. Because, I mean, we had a Python interface in Trilinos for, I don't know, 20 years, and most of the time it was broken because somebody changed something in the C++ interface and nobody bothered to update the Python interface. Or the developer responsible for the Python interface was not the same developer responsible for the C++ interface, all sorts of issues. So we want something that's a bit more automated. What we're using currently for this is a tool called Binder. And essentially what this does is it leverages Clang and LLVM tools to parse the source code and then auto-generate these interfaces, essentially this sort of like block up here for all sorts of like methods and functions and classes that it can discover. So just to give you an example how this works, I'm showing you the configuration files for tpetra. So let me see if actually anything executes on here. And if I can do this with one hand. So this is, I'm just cutting out. Essentially, the way it works is you give it a couple of header files, and it then greedily goes through a tree and like looks for all the other includes in that file and just sort of like traverses through everything it can find. And then you can sort of like drive it to like include or exclude certain things by like whitelisting or blacklisting things, or you can also selectively add on certain functionality to certain classes. So for example, this is the file that I'm giving it to process tpetra. It's essentially just all the auto-generated ETI files that tpetra already generates for us. So that's relatively easy, and it will start like crawling through all of tpetra starting from these files. So that's one part. The second part then is the configuration file associated with tpetra. And this is what we have for that. Essentially, we say, okay, you're supposed to include everything in the namespace tpetra. We want to add some sort of like special code for Cocos initialization. We also have a couple of convenience functions that we sort of like tag onto the generated classes. And there's a couple of namespaces, I mean, details namespaces or implementation details that we simply like trim out again because we don't want our users to see that. And that's really all that is in terms of configuration for this. Now, I mean, there's always some issues with building this. I mean, we essentially now, instead of writing individual wrapper functions, we have to deal with sort of classes of problems. Initially, we dealt a lot with things like, oh, somebody managed to have a declared function that never had an implementation, and wrapping something like that with a tool that's greedy obviously creates a problem. So in some sense, this also leads to better code quality. We're effectively finding all the sins that somebody committed somewhere in Trilinos because we're actually trying to like link and build against all of these things. All right, so that was sort of like the generic, how do we build our interfaces? Now, what does that look like? I mean, I'm a solvers guy. I want to like show off some solvers problem. So what we'll do is we'll try to, in this notebook, solve a linear system. So anybody trying to do this? Has anybody gotten a note with this? Yes? Perfect. Okay. This actually works. This is great. Okay. So I had to write some special code so that actually all the standard out is like redirected into the notebook. But now we can essentially play this game of like introducing, say, students or like now you're my guinea pigs, into how tpetra or how Trilinos sort of like works and how you can solve a linear system that you solve up within the context of this notebook. So we'll just start by importing, essentially like including tpetra from the PyTrilinos2 package. One difference that we see immediately is, well, I mean, C++ is templated, and we're big users of templated classes. And Python does not have templates. And the way this is handled is that simply all the template parameters of a given class are being appended to the name of the object. So instead of, say, getting our like tpetra a map with our template parameters, we are getting something like that, which I mean is just ugly. We don't want to like handle something like this. I mean, it's nice that it's all exposed, but we want something that's a little bit better. And so what PyTrilinos2 now actually does is that it includes a couple of convenience functions that allow us to deal with templated classes in a sort of more C++ lookalike sort of way. So instead of like specifying this really long name here, we can specify something that takes the different template arguments. And this also allows us to then essentially like use default arguments and do something that's really quite a lot shorter. So that's how we were to use tpetra and generally templated classes in PyTrilinos2. All right. So if we want to get some help, because now we want to like set up our linear system and all that, we can call the help function on it. It's going to tell us a whole lot of scrolling is really not great on this. It's going to have some auto-generated help for all the different methods that we wrapped for our classes. In principle, it can consume doxygen strings out of the C++ code. This doesn't always seem to be working reliably. So for whatever reason, we're getting a doxygen string doc here. And I checked that this class is actually way better documented than what shows up in the Python class. So there's still some small things that I need to fix there to like make sure this works a little bit better. Let's see. Okay, but we can get started and sort of set up our linear system now. This works with other sort of like typical Python packages. So for example, for MPI, we import MPI for Py. And this can then just be passed into the typical like Theros objects that you would be using. So the first thing is we want to set up our linear system. So we set up our map. Obviously, all the sort of keyword arguments or named parameters, you can just use that from Python directly. It pulled all of that from C++. So here I have my little sort of like 1D Laplacian function using T-Petra, sort of like the typical calls to set up a linear system. At the same time, you could also sort of pass in, if you already have a system in Python, you can pass it into and sort of like wrap it with the linear algebra, with our sparse linear algebra, without actually having to copy anything. You can just pass in the buffer. All right, so we'll set up our linear system, our T-Petra matrix A, and we also generate two vectors that we will use for the right-hand side of our system and for the solution. And, well, we want to solve that. First thing is I just check the residual norm, just checking that, making sure that I'm not cheating you, and the residual norm is actually non-zero. Yes, we haven't solved the system yet. All right, so we want a solver from Trilinos. And what we're going to be using is, I mean, we have a ton of different solvers. A lot of them are exposed through this sort of generic solver interface called Stratamikos. And this is using a sort of generic linear algebra interface as well. So we'll take our T-Petra objects, the actual linear algebra objects that we have, and we wrap them into a different format. So this, I wrote a little helper function for that here. That's essentially taking all of these objects and just doing a wrapping of those. Then we get the Stratamikos library, which will then help us construct all these linear solvers and preconditioners once we get to that. All right. I should say that all our solver options, typically we do represent them as a terse parameter list. Coming from a Python world, you can see this sort of as a Python dictionary with a couple of nice additional features. We'll see there's some amount of like validation of the parameter list so that you can like stick in absolutely anything, and we'll leverage that in a second. So we'll generate a parameter list, and the only parameter that we're really passing in there is just saying we want a linear solver that is named Amazos2, which corresponds to the package for direct solvers. All right, so we've done that, and we printed that as well, and yeah, there's only one parameter in there, and so far it says unused because we haven't actually used this parameter list. This parameter wasn't consumed by anything yet. And then we can actually construct a solver for our given now wrapped linear system A. So we'll do that. And this is going to give us a solver. And then we can use another method to just apply the solver to our given right-hand side and solution vector. And it tells us that we actually converge, which is great because that is a direct solver. So it would be very dissatisfying if this didn't converge. So let's just double check because we really don't want to trust it. And we see that now our residual is 10 to the minus 10. So that looks about right. Now, there's obviously a lot of different other solvers in Trilinos, and it's sort of tricky sometimes to discover what sort of solver options are actually available. So here's a little helper function that I wrote, and what that does is essentially it pulls out the validation information out of this parameter list and can then tell us, okay, what are the available solvers that we can actually choose? What can we currently actually use from Trilinos? I just scrolled a whole lot all at once. So I'm essentially just calling, so I'm getting the valid parameters out of this linear solver builder object, and then I'm printing all the valid options for different values of the parameters that are in this parameter list. And then I'm just printing all of that out. So currently what we're seeing is, if I can scroll, so currently there are two linear solvers that are available. And then I'm printing for each of them what the available, or two linear solver packages, and for each of them I'm printing the linear solvers that are available in there. So in Amazos2 that I totally misspelled, we currently have two direct solvers. There's KLU2, which is the built-in direct solver, and we have a LAPACK interface if you care to solve a dense system. Then we also have Belos, which is the collection of Krylov solvers, and for that there are a couple of different options, GMRES variants, CG variants, and a couple of more sort of exotic solver options. I'm also printing what we currently have available in terms of preconditioners. We see there's the non-preconditioner, which means don't do any preconditioning at all. And there is IFPEC2, which is this sort of simple single-level algebraic solvers. And if we then print what all of the options are that this ifpack2 package actually takes, well, there's a whole lot of different options, like relaxation solvers like Jacobi and Gauss-Seidel, and polynomial preconditioning, and different ILU variants, and a lot more. So there's already a bunch of different options. Okay, so let's solve our system instead of using a direct solver, using a Krylov method instead. It's the same approach as before. We have this parameter list where we pass in all these parameters, all these different string combinations and integers and whatnot. It's a little bit longer now because, I mean, all of these packages take quite a lot of options, especially the iterative ones. So essentially what we're specifying is now, give me a solver from the Billers package, make it a block CG solver, and precondition all of this with, let's see, nope, either direction. Precondition everything with ifpack2, and if in ifpack2 use a relaxation preconditioner, which in this particular case is going to be a Jacobi method. Okay, that's a very long parameter list. And I mean, obviously, normally you would like save all of this into some XML or some YAML input deck and not have this directly just in your code. And then we zero out our solution vector, and then we play the same game again that we just played before and try to solve the system. This time we get a bit more output. And oh no, we saw that actually our system was too difficult to solve with this particular preconditioner, with this Jacobi preconditioner. We didn't actually converge all that well. So that's sad. So we need something that's a bit better than just a Jacobi preconditioner. And so we'll enable some more advanced preconditioners in our solver factory. So we enable Mulu, which is the package for algebraic multigrid. And we'll play exactly the same. Did it paste something in there now? That's obviously not great. Okay. We'll play the same game again, only this time we'll specify that we want a algebraic multigrid preconditioner. We're not passing in any additional parameters there. I mean, AMG takes quite a lot of different options, and I don't want to scare you away yet. So we'll pass that in, and we'll play the same game again, and this time it manages to solve it in 7 iterations. So that's great. We obviously also have, like, we can combine this with different packages that have nothing to do with Trilinos. So we can pull data out again out of these tpetra objects. So just to demonstrate that, I'm importing matplotlib here, and I'm essentially just pulling out the data of this vector, of essentially out of the solution vector, and I now just use some Python tools to plot the solution. I mean, it's a super simple problem. For instance, it's a 1D Poisson problem. This is just to demonstrate that this works. Now, one thing I haven't mentioned so far is that in this Jupyter notebook, everything is on a single MPI rank. There are ways of running Jupyter notebooks with several MPI ranks. It's a bit clunky, and so I don't want to really use that. So instead, what you can do, if this is, if you want to quickly try this out, there is a whole, actually like a Python script somewhere in this container that you can run. So I'll try to do this live and see how bad I fail about this. So we can also just open a terminal in this container. And let's see about that. So it's somewhere in my build tree. So we can it's essentially the same example, setting up some linear system and then solving it with different solve options. And we can solve that as well. And it essentially like runs through and gives us some indication of whether the problem was solved or not, and also gives us the usual timing information. So this is just, I mean, this is sort of work in progress. There's still a lot of additional features that we want to add to this. Currently, I mean, it obviously covers a lot of the like linear solver infrastructure. I'm working on getting some more of the discretization tools into this. And I mean, it's a relatively nice way of very quickly showing off something that just runs whilst hiding all the sort of details of how to actually build this or configure this or doing any of that. So that's all I have. Thanks.
Any questions?
Have you looked at, so there's PyTrilinos, right? Have you looked at using PyTrilinos with?
It seems they essentially are using, my recollection is they're using PyBind 11 as well. And yes, we could sort of like combine that for getting access to like the sort of like the views or arrays that they have, instead of like directly shipping it to host. Because I mean, this is essentially what this is doing. If you access something, then you just get the host view. It could be combined, yes.
Did you dare push this all the way to mini-EM?
So I mean, what do you mean by mini EM? I mean,
just the higher level packages. Like
I mean, the goal is to, I mean, essentially what I'm currently working on is I started from Panzer and then getting whatever dependencies get pulled in through that. So I think Stick now, at least for the sake of Panzer, seems to work for this. I still have some like shards issues that I need to like get rid of, and there's some problems in Panzer. But yes, I mean, this is the goal. Because I mean, effectively, if Panzer is, but if Panzer is really a lot of glue code that like puts different packages together and combines them into an application, but nothing, I mean, apart from, I mean, there's assembly in Panzer that has to run fast, but there's a lot of things in Panzer that are not performance critical. And doing them in Python would be really nice to sort of like quickly, I want to throw together my application for solving, say, a heat equation with some sort of like, I don't know, like PDE constraint optimization. None of this really has to like run in C++. I mean, the underlying kernels, yes, but the combination of the different parameters and all that, I mean, Python can do that. But we'll see how long that takes. So, I mean, it is, all of this is now in Trilinos, and there is a spec package for Trilinos. However, I think we have already covered that the spec package for Trilinos is not necessarily the most amazing spec package out there. So, I mean, if you want to build all of this, you totally can using spec. I would not recommend it, but that's a general Trilinos problem. Currently, there's no app using it. We've done something similar for the role package in Trilinos, sort of like as a first testing ground, and they've had a lot of success generating sort of tutorial materials and giving this out to university collaborators because they don't want to install Trilinos or like configure even like a C++ code, but they can pip install a Python package, and so we essentially packaged this all up, gave them a single file. They have that on their homepage, and they're very happy about that. And I mean, for an actual application, at some point, you don't need a Python interface to drive an actual application. You can do this like from C++. Once you set in how you want to run your code, this is fine. You don't need Python for this, or you don't need to use Python for this.
But I suppose you could like target Phoenix or Firegrid.
Oh, you totally could, yes. And I mean, this is the other idea that this makes it easy to integrate this code into some other packages that are a bit beyond the traditional Trilinos horizon.
Okay, very
Cool.
cool. Well, that ends our session. Let's thank Christian again.